Hi and welcome to one and all. Today we are going to discuss about the fourth module of analytic number theory, and in this module we will be studying on periodic arithmetical functions and Gauss sums. In this first lecture, I will be talking on the functions periodic modulo k and the results associated with this. Let us go to the definition of a function's periodic modulo k. That is, let k be a positive integer and arithmetic function f is said to be periodic with the period k, or we say it is as a periodic modulo k if f of n plus k is equal to f of n for all integers n. This means that the function f repeats after k period. That is, the function will be behaving as f of n after k period. That is, f repeats after every k period. It is clear that if k is a period, so is k plus k, k plus 2k, k plus 3k. That is 2k, 3k, etc. And that is, this can be said that if k is a period, so is mk for any integer m greater than 0. The smallest positive period of f is called the fundamental period. I hope you understood the concepts. Now let us go to some examples of functions periodic modulo k. Let us see the first example. That is, you have already studied about the Dirichlet characters. The Dirichlet characters mode k are periodic mode k. And it is evident from the theorem which you have learned earlier that there are 5k distinct Dirichlet characters modulo k, each of which is completely multiplicative and periodic with the period k. That is, we have chi mn is chi m times chi n for all mn, and chi of n plus k is chi n for all n. Now we will go to another example, that is the greatest common divisor GCD of n and k regarded as a function of n are periodic mode k. That is, if we take the function as the GCD of two numbers, then we can see that this is a periodic function modulo k. Here we can see that if we take an example 2 6, if we take the GCD of 2 and 6, it is 2. Then clearly the GCD of 2 plus 6 and 6, that is 8 6, is also 2, and 2 plus 12 and 6 is also 2, so and so on. So clearly GCD nk is periodic. Let us take another example. The exponential function f of n is equal to e raised to 2 pi I mn by k, where m and k are fixed integers, is a periodic function, periodic modulo k. It is clear that we have already studied about the kth roots of unity. You can see that e raised to 2 pi I m by k is a kth root of unity, and f of n can be seen as the nth power of e raised to 2 pi I m by k. And clearly, so if we take f of n plus k, you can see this as e raised to 2 pi I m by k whole raised to n plus k, which is equal to e raised to 2 pi I m by k whole raised to n times e raised to 2 pi I m, because k gets cancelled, and finally we will end up with it e raised to 2 pi I m by k whole raised to n, which is fn itself. So f of n plus k is again f of n. Thus f of n is equal to e raised to 2 pi I m n by k is a periodic mode k. Since this f of n equal to e raised to 2 pi I m n by k is periodic, we can say that any linear combination of this function will also be periodic. So if we take some suitable scalars cm, then we can see that cm times e raised to 2 pi I m n by k is also a periodic function modulo k. So these sums are, we usually call it as a finite Fourier series. Now let us quickly see one theorem associated with this. that for a fixed k greater than or equal to 1, let g of n is equal to sigma m is equal to 0 to k minus 1 e raised to 2 pi I m n by k. Then we can see that g of n is equal to 0 if k does not divide n, and k if k divides n. Here we have to show that if g of n is of this type of a summation, then g of n can be written as 0 if k does not divide n, and k if k divides n. Now let us see the proof of this result. Since g of n, we can see that if we replace this e raised to 2 pi ai m n by k, if we replace this as if we give a substitution that x is equal to e raised to 2 pi I n by k, then we can clearly see that this is nothing but a sum of the terms in a geometric progression. That is, g of n can be written as summation m equal to 0 to k minus n x raised to m, where x is e raised to 2 pi I n by k, and this is 1 plus x square plus etc x raised to k minus 1. Now if we use the result of the end sum to end terms of a geometric progression, that is 1 plus ar square plus etc ar raised to k minus 1, the result will be a times r raised to k minus 1 by r minus 1 if r is greater than 1, and a times 1 minus r raised to k by 1 minus r if r is less than 1. So here, since it is clearly given that this k is greater than or equal to 1, so we have to use the first result, and we will get g of n is equal to x raised to k minus 1 by x minus 1. Since here a is equal to, in our result, a is equal to 1, so g of n is equal to x raised to k minus 1 by x minus 1 if x not equal to 1. And if x equal to 1, then this summation will become summation m equal to 0 to k minus 1 1. So this is nothing but the sum, this sum will become k. So if x is equal to 1, we have k. Now we know that since x is equal to e raised to 2 pi I n by k, and if I take the power x raised to k, you can clearly see that this k will get cancelled, and you will get e raised to 2 pi I n, and this is nothing but this will reduce to 1. So x raised to k, if you take x raised to k, this term will be reducing to 1, and if this x raised to k reduces to 1, you can see that this x raised to k will be 1, and this term will become 0. So x raised to k minus 1 by x minus 1 becomes 0. And if x, so we can see that if x is not equal to 1, so this is the case when x is not equal to 1, in which case we this is only possible when k does not divide n. That is because if x equal to 1, then we have only k. That this happens only when k divides n. If this is not equal to, x is not equal to 1 only when this n does not k does not divide n. If n if we can divide n by k completely, then this will reduce to, this term will reduce to 1. So since so in that case, we can say that if we have, if x is equal to 1, that this will happen, if x is equal to 1 will happen only when k divides n, and so we have the result that g of n is equal to 0 if k does not divide n, and equal to k if k divides n, and thus we have proved the theorem. Hope you have understood. If you have any comments or questions, you just drop me in the message box.